Today we will study the new chapter, chapter 2, Electrostatic Potential and Capacitance. In the previous chapter we have studied electric charge, electric field, electrostatic force, Coulomb's law and Gauss law and their applications. Now in the previous chapter we have studied two important concepts, that is electric field and electric force. Those are vector quantities. Now here are going to study two concepts, that is electric potential energy and electrostatic potential. These two are scalar quantities. Okay, in first PUC we have studied that. In the chapter 6 we have studied work done. Now what is the work done? So work done is, it is the dot product of force and displacement, or we write it as FD cos theta. It is a scalar quantity we have studied. And in the 8th chapter we have studied gravitational potential energy. And it was denoted by the letter U. So what is the gravitational potential energy that we have studied? We have a gravitational force. The amount of work done in moving an object or in lifting an object from one point to the another point. For example, let me consider this is the earth surface. Here we have an object which is on the surface of the earth, that is ground, of having mass m. Now I am going to lift this mass to a particular height h. What I have to do? I have to apply an external force in order to lift this mass from ground to the certain height h. Now we have applied a force against the gravitational pull. Now this force has done work on the object. Now this work done is stored as gravitational potential energy in the object. Now that gravitational potential energy stored in that object that we have studied already is given by force into displacement. Force is m into g and the displacement is h height. Now what happens when you remove the external force applied to this object? Now thus that object starts falling down. That means whatever the gravitational potential energy stored, it gets converting into kinetic energy. The object starts falling, therefore it is going to acquire the kinetic energy, and obviously what happens? Potential energy goes on decreases. So therefore their sum remains a constant. That we have studied the conservation of mechanical energy that we have studied. Now this work has to be done, whatever the work done by the external force, in order to moving an object from one point to the another point against either the gravitational force or the case of a spring force, that is stored as potential energy in the object. Now that potential energy we have called it as gravitational potential energy. Now similar to this, that of this gravitational potential energy, in electrostatics, a charge is going to possess an electrostatic potential energy. That concept we are going to study. Now in the case of gravitational potential energy, we have a force between two point masses is given by capital G m1 m2 divided by r square. M1, M2 are the 2 point masses. If they are separated by a certain distance r, then obviously we have a gravitational force of attraction between those 2 point masses, and is given by the simple relation. In the previous chapter we have studied, if you have 2 point charges Q1 and Q2, if they are separated by a distance r, then obviously we have an electrostatic force. Let me write the gravitational force as Fg and electrostatic force as Fe. That is equal to, let me write some constant k, that is we know 1 divided by 4 pi epsilon naught into, now masses are replaced by the charges. M1 is replaced by charge Q1 and M2 is replaced by the charge Q2, and the distance of separation, if I take the r as the distance of separation between the 2 point charges. Now look here in these two mathematical form of the gravitational force and the electrostatic force. They resemble in a mathematical form. Masses are replaced by charges, and only difference is the proportionality constant. Here we have capital G, that is a universal gravitational constant. In electrostatic force we have K, and we know that K is given by 1 divided by 4 pi epsilon naught. Its value is 9 into 10 to the power of 9, we know. Now these two forces are also inverse square dependence. That means they are inversely proportional to square of the distance of separation, these two forces. Therefore, with this similarity, we are going to study electrostatic potential energy in electric field similar to that of gravitational potential energy in gravitational field. Now for that one, and one more thing, now this spring force and gravitational force, they are conservative forces. What is the meaning of conservative force? The work done by these force, it depends only on the initial and the final point and not depending on the actual path of movement. So similarly, this electrostatic force is also a conservative force because work done by the electrostatic force is going to depend only on the initial and the final point. It is not going to depend on the actual path of motion. Okay. Now let me consider some charge here. We have some charge, positive charge Q. Okay. Because of the charge, we have an electric field around it. We know in the previous class. Now let me take one more charge, a test charge. Let me call it as a test charge. Assume that it is also a positive charge. So here we have taken a source charge, capital Q, a small positive test charge. Obviously, there is a repulsive force. Let me consider this small test charge at a point R. It is at a point R. Now, I have to bring this test charge from point R to some point P. Point R to some point P here. I have to bring it. Now look here. This is positive charge. This one is also positive charge. Obviously, there is a electrostatic repulsive force. If I have to bring this charge from R to P, there must be a repulsive force. Therefore, I have to apply an external force. Let me call that one as F external force. Why I have to apply? Because obviously there is a repulsive force. In order to overcome that repulsive force, I have to apply an external force in order to bring that unit positive test charge from point R to the point P. Now this external force what we have applied, it should be such that it is exactly equal and opposite to the electrostatic force between the two charges. it should be equal, but opposite in direction to the electrostatic force. That means we are not supposed to accelerate the charged particle there, that charge. We are not going to apply the force such that the charge should not be get accelerated while moving from R to the point P. Should remember this very important point. So whenever we apply an external force from moving the charge from R to P, work has to be done. Therefore, what is the work done? Work done in moving the charge from R point to the P point is equal to, we obviously know that it is force external multiplied by the distance. If I take that small distance as dr, we are moving through a small distance dr. F external into dr. But here, this force is not a constant one. It is variable. Now look here, this electrostatic force is inversely proportional to the square of the distance. What is the force between this charge which is at R and the charge Q which is at fixed point? Now at the point P, whenever it moves to the point P, the distance decreases. Obviously, the electrostatic force increases. So that means we are applying an external force which is a slightly variable one. So therefore, we have studied in the first PUC, the variable force, work done by the variable force is calculated by using the integration notation. That is the initial point R to the final point P. If the force is constant, so simply we write F external into dr. Since here the force is variable, so we have to work out the work done by using the integration sign. Therefore, WRP is the work done in bringing the point charge, test charge from R to P. Now, this work done should be equal and opposite to the electrostatic force. So, therefore, I will write this WRP is equal to integral of R to P. Now, X external is replaced by FE, negative sign, with a negative sign. So, negative sign is going to indicate the direction only. Now, this amount of work done is stored as the electrostatic potential energy. This amount of work done is stored as the electrostatic potential energy of the charge Q in the presence of any arbitrary field configuration. Now, let me write that one as potential energy. Electrostatic potential energy, U can be written as it is the work done minus Fe external into dr. So that is the potential energy of the charge. Now here one more thing you should remember. We have to choose the charge Q so small that it is not going to disturb the source charge. That thing you should remember. Now let me define potential energy difference. Here potential, this is the potential energy, expression for the potential energy. Now potential energy is not an important concept, significant concept. The significant concept is the potential energy difference between the 2 points. That means that point charge is having potential energy at all points in the presence of an external field configuration. So we have a field here, we have a charge, because of that one you have an electric field around it. If I take one point charge inside that field region, that point charge possesses a potential energy. So here that potential energy is not important. The difference of potential energy is a very, very important one. Now let me define electrostatic potential energy difference. Now potential energy is given by this relation. it is the amount of work done. The potential energy difference is defined as the amount of work done in bringing by an external force in bringing a charge from one point to the another point in the presence of electric field due to any charge configuration. So therefore, we can write the potential energy difference delta U is equal to, if UP represents the potential energy at the final point P and UR represents the potential energy at the initial point R, then UP minus UR is called the potential energy difference, and this should be equal to work done in moving the charge from R to P. So that is the definition of electrostatic potential energy difference. Now we are bringing the charge from R to P. Now consider a charge is brought from infinity. That means we are extending this initial point to infinity. Why we are extending here? The potential energy is taken to be 0 at some arbitrary point. Here we are choosing that arbitrary point as infinity. We are taking infinity is the point at which the electrostatic potential energy is 0. So therefore, if I extending the point R to infinity, then what I am going to get here, delta U is equal to, it is UP minus U infinity at infinity, and similarly the work done becomes from infinity to the point P. At infinity we have taken potential energy is 0. So therefore, W infinity to P, work done from moving the charge from infinite distance to the point P, is nothing but potential energy. It is the potential energy of that charge at the point P. Now from this one we can define potential energy at a point, potential energy of a charge at a point due to some other external electric charge or electric field configuration. The potential energy of a charge is defined as the amount of work done in bringing that charge from infinity to the given point is called as potential energy. It is potential energy. Potential energy. Now let me define one more quantity, potential. Potential energy, it is denoted by the letter U. The potential is denoted by the letter V. Now work done is simply force into displacement. Now in electrostatic force we have, it is Q into E. Force on a point charge is Q into E. Therefore work done depends on the charge Q. It is charge dependent. Now let me define one more quantity which is charge independent. So that means it is not depending on the test charge. For that one I have to do divide the work done divided by the charge. Then I am going to get E into some distance D. Now this quantity which is independent of the test charge gives the definition of electrostatic potential. So therefore, the electrostatic potential at a point due to the external field configuration is the amount of work done in bringing a unit positive charge from infinity to the given point. Now this definition is similar to that of potential energy definition, But in the case of potential energy, we are bringing a charge from infinity to the given point. But in the case of potential, we are bringing a unit charge. That means Q is equal to 1 here. We are bringing a unit test charge from infinity to the given point. Now that defines potential, electrostatic potential. Now, what are the SI units of this potential energy and potential? Now, SI unit of potential energy, it is nothing but joules, and SI unit of potential, it is volt. And one more thing, this work done here, it is not depending on the path of motion of the charge. So this work done in moving from R to P, if I bring in this path, if I bring in this path, whatever it may be the path, it is independent of path. Work done is independent of path. Therefore, the electrostatic force is also a conservative in nature. It is conservative force. That means work done not depends on the path. It depends only on the initial and the final point. So in the same manner here also, the potential is not very important. It is the potential difference is very, very important. Similarly, we can define electrostatic potential. This is electrostatic potential energy difference. Now this is electrostatic potential difference. Then what is that meaning? How you define that one? Amount of work required to bring a unit positive charge from one point to the another point in the presence of external field configuration. Therefore, potential difference between 2 points can also be written as potential at the point P minus potential at the point R. That should be is equal to potential energy at P minus potential energy at R divided by the charge. Hence, potential difference between 2 points is the amount of work done in bringing a unit positive charge from one point to the another point. Now, whatever the remarks we have made while studying this potential energy, the same remarks holds good even for this electrostatic potential. Now we will derive an expression for electrostatic potential due to a point charge. Now for that one, consider a positive charge capital Q at the origin O. Because of this positive charge, there is an electric field outside. Now let me consider some point P at a distance R from the charge. At that point P, we are going to work out what is the electrostatic potential due to this capital Q charge. For that one, I have to bring a unit positive charge, that is plus 1 coulomb. Plus 1. It is a unit positive charge. Coulomb is a huge quantity, but unit positive charge, we are taking it as a 1 coulomb. Now, the potential at P is defined as the amount of work done in bringing a unit positive test charge from infinity to the point P in the presence of field due to the charge capital Q. So in order to work out what is the work done in bringing from infinity to point P, we will consider some arbitrary point here R. Let me take it as some arbitrary point R, which is at a distance, let me consider it as X. Some arbitrary point we have chosen at a distance X from the capital Q charge. Now unit charge is at R. At R, the force between these two charges is given by the electrostatic force is equal to the general formula 1 divided by 4 pi epsilon naught Q1 Q2 by R square, general formula. Now Q1 is the capital Q charge, Q2 is, it is a unit charge, 1 divided by, now the distance here it is x, therefore I am writing it as x square. So as and when the unit positive charge is placed at the point P, R, at the point R, the force between those two charges is given by this simple relation. Now I am displacing this unit charge through a small distance dx, small distance dx against the field direction. Then obviously work has to be done. Work done in moving the unit positive charge through a small displacement dx is dw is equal to minus f into dx. Okay. So minus sign, why we are getting minus sign? Because work has to be done against the field direction. Now this is a small amount of work done. Now our aim is to find the potential at P. According to the definition, the amount of work done in bringing that unit positive test charge from infinity to the point P. So that is the total work done is obtained by integrating this one from infinity to the R into dw. Now that is equal to from infinity to R minus of f into dx. Now substitute for f here, I am going to get, so let me take the minus sign outside, infinity to R 1 divided by 4 pi epsilon naught into q by x square into dx. Okay. Now taking out the constant terms, 1 divided by q divided by 4 pi epsilon naught is constant, we taken it out. Now integral infinity to R 1 by x square with respect to dx. Now we have to integrate this one. We know the integration formula, that is integral of x to the power of n with respect to dx is equal to x to the power of n plus 1 divided by n plus 1. That is the formula. Now here we are having 1 by x square. If I take the x square to the numerator, it becomes x to the power of minus 2. So therefore, here integral of x to the power of minus 2 with respect to dx, it becomes x to the power of minus 2 plus 1 divided by minus 2 plus 1. Now simplifying that one, we are getting x to the power of minus 1 divided by minus 1, or it is equal to minus 1 divided by x. That is the integral part. Okay. So therefore, work done is equal to minus q divided by 4 pi epsilon naught. Now integration of this one is minus 1 by x. It is minus 1 by x from infinity to the point R. Now take this minus sign outside, minus of minus, it becomes plus. Therefore w is equal to q divided by 4 pi epsilon naught into, first apply the upper limit, that is 1 by R minus the lower limit 1 by infinity. We know that 1 by infinity is 0. So therefore the work done is given by 1 divided by 4 pi epsilon naught into q divided by R. But according to the definition, now this amount of work done in bringing a unit positive charge from infinity to the given point, it defines electrostatic potential at the point P. So therefore, the electrostatic potential at the point P is given by the relation 1 divided by 4 pi epsilon naught into q divided by R. That is the expression for potential due to a point charge at any point P which is at a distance R. Now look here, this potential is inversely proportional to the distance of the point. And one more relation we are going to get between the potential and the work done. Now work done is equal, that we have work done divided by the charge is the potential according to the definition. Work done divided by the charge is the potential, or work done is equal to Q into V. We are getting one more important relation. Work done is equal to charge multiplied by the potential. And that formula we are going to use while solving some problems. We know that the electric field is given by the relation 1 divided by 4 pi epsilon naught Q divided by R square. And the potential is given by the relation E is equal to 1 divided by 4 pi epsilon naught. So Q divided by R. Now compare here. The electric field is inversely proportional to square of the distance. The potential is inversely proportional to the distance only. Now let me represent these two graphically. The variation of electric field and potential with respect to the distance of the point. Now along the x-axis we are taking the distance r. Along the y-axis we are taking the two quantities. One is the field and another is the potential. Now first graph is potential. This is potential V. Now the second graph that I am representing it by the dotted lines. That is the electric field. So dotted line represents the electric field and the curved straight line, that is solid lines, represents the potential. Now we will work out on simple problem. Calculate the potential at a point P due to a charge of 4 into 10 raised to minus 7 coulomb located 9 centimeters away. Second part, obtain the work done in bringing a charge of 2 into 10 raised to minus 9 coulomb from infinity to the point P. Now we have a charge here, some positive charge at some point O. Now we have to find the potential at this point P, which is 9 centimeter. Now the distance is given in 9 centimeter, we have to convert it into meter. We have to calculate the potential. What is the potential at that point? And also we have to calculate what is the work done in bringing the another charge. Okay. Now solution. Now the source charge capital Q is given. Capital Q is placed at the origin. It is 4 into 10 to the power of minus 7 coulomb. Now distance of the point, that is small r, it is 9 centimeters away. Now convert it into meter. It is 9 into 10 to the power of minus 2 meters away. Now we have to calculate what is the potential at that point. The first part. Now the potential is given by V is equal to 1 divided by 4 pi epsilon naught into capital Q divided by R. That is the general formula. Now substitute the values. Now value of 1 divided by 4 pi epsilon naught, we know it is 9 into 10 to the power of 9 coulomb square per Newton meter square. And charge Q, it is 4 into 10 to the power of minus 7 divided by 9 into 10 raised to minus 2. So simple calculation. So 9 get cancels. Therefore the potential is 4 into 10 to the power of minus 2, it comes to the numerator, it becomes plus 2. 9 plus 2, it is 11. 11 minus 4, 11 minus 7, it is 4. So 10 to the power of 4 volts. Now this is the potential at the point P due to the charge 4 into 10 raised to minus 7 coulomb. This is part A. Now part B. Now we have the potential at the point P. Now we are bringing a charge q is equal to, small q is equal to, so 2 into 10 raised to minus 9 coulomb from infinity to the point P. Then what is the work done? Now that work done we have to work out. We know the simple relation, the work done is equal to charge multiplied by the potential. Now here which charge we are going to take? We have to take the charge which is to be brought from infinity to that point. We are not supposed to take the charge at the origin. Okay? Yes. Now this is equal to, now the charge which is we are bringing is 2 into 10 to the power of 9, 2 into 10 to the power of minus 9, 2 into 10 to the power of minus 9 multiplied by the potential due to this source charge at that point. It is 4 into 10 to the power of plus 4. So simply we get 8 into 10 to the power of minus 5 joules. Now this amount of work has to be done in order to bring this 2 nanocoulomb charge from infinity to that point P.